Yes.
Okay. So, okay. So, hello everyone. I'm Filipe and I'm with the Instituto de Telecomunicações de Aveiro. And I'm going to present the work that we've been doing on introducing energy and carbon-aware orchestration mechanisms into open source MANO to improve the sustainability of ICT operations. This talk will be divided into three parts. So first, I'll introduce the motivation behind this work and explain how the current trajectory of ICT systems is creating a need for more sustainable mechanisms. Next, I'll describe the new energy and carbon-aware mechanisms we integrated into open source MANO. And finally, I'll present a case study we conducted to validate our solution, our implementation. So starting by briefly looking at the motivation behind this work. In recent years, climate change has been worsened by rising greenhouse gas emissions. In response, countries and organizations and companies have established low carbon targets to align with the Paris Agreement set by the United Nations in 2015. Telecom companies, in particular, have committed to reducing their carbon emissions by 50% by 2030, with some aiming for reductions of up to 90% in 2040. Achieving these goals requires operators to rely more on renewable energy sources and adopt sustainable mechanisms across their operations. However, the rapid growth of AI adoption, as well as this growing data traffic, have significantly increased data center energy consumption. In 2023, data centers consumed an estimated 300 to 380 terawatts per hour of electricity. However, by 2030, it's projected the electricity consumption is projected to rise to between 600 and 800 terawatts per hour. To better understand these values, 800 terawatts per hour is equivalent of 2% of global electricity generation. Current power generation methods and existing infrastructure are not prepared to handle this level of demand. As a result, many ICT organizations are turning to fossil fuels to meet the energy needs of their data centers. This trend highlights the need for new sustainable mechanisms designed to reduce the energy consumption and carbon footprint of ICT infrastructures and services. These circumstances define the scope of this work. It is developed within the Exigence project, an European initiative aimed at reducing the environmental impact of ICT systems, particularly in the context of next-generation mobile networks. The contribution from Instituto de Telecomunicações focuses on introducing energy and carbon-aware mechanisms into open-source MANO. These are mechanisms designed to reduce the energy consumption and carbon emissions of both services and the underlying infrastructure. So now let's take a look at the technical implementation of the proposed mechanisms into open source MANO. So open source MANO does not include any sustainability-driven orchestration mechanisms by default. For this reason, its operation had to be extended to incorporate these capabilities. To achieve this, we introduced a new model named the Echo Control module. It is deployed alongside the existing OSM modules and is responsible for handling all sustainability-related orchestration functions. In this work, two different orchestration mechanisms were added to open source MANO. The first is a service throttling mechanism, which adjusts the performance level of a service. And the second one is a spatial shifting mechanism, which deploys or migrates the service to different geographic locations according to some criteria. To implement the service throttling mechanism, we adopted a concept defined in the ETSI specifications, called virtual energy aware states. These states represent different operational modes that a network service can transition into. Each state specifies a particular resource configuration, which corresponds to an expected energy consumption level and performance level. To support virtual energy aware states in OSM, we extended both the virtual network function and the network service information models to include the fields defined in the ETSI documents. We also modified the NBI. We extended the NBI so that the network service instantiation and update endpoints now allow users to specify the virtual energy aware state that the NS should be deployed or transition into. The Echo Control module is responsible for storing the state's configuration of each deployed network service, as well as tracking which VIMs are assigned to each service, and executing the logic required to apply the state's transitions. It interfaces directly with the VIM to enforce the corresponding resource configuration changes. Here on the right, we can see an example of a VNF descriptor that includes the state's definitions. These are highlighted. The states are highlighted in red. These are primarily CPU-related configurations, such as clock speed, which determines how many operations the CPU can execute per second. The power states, which specify different CPU operating modes, each with distinct power consumption levels. And finally, it defines CPU pinning strategies, which define how virtual CPUs are mapped to physical cores. The VNF descriptor shown supports two states, each designed for a different operating scenario. The first state represents a standard operation with high performance requirements, reflected by a higher clock speed, enabling more operations per second. The second is a green mode, focused on reducing energy and power consumption. It uses a lower clock speed, which decreases the performance, but also reduces power usage by lowering the voltage required to switch CPU transistors. By interacting with the northbound interface, the NBI, a user can switch the service between these states based on the system needs or external conditions, while taking into account the trade-off between energy and performance. The second proposed mechanism is a spatial shifting mechanism. Its goal is to enable sustainability-driven deployment of network services across different VIMs. To accomplish this, OSM must have access to environmental metrics associated with each VIM. The Echo Control module is responsible for collecting these metrics, specifically power usage effectiveness, which reflects the infrastructure's power efficiency, and the carbon usage effectiveness, which represents the carbon footprint of the infrastructure, where a lower carbon usage effectiveness, or CUE, indicates a lower carbon impact. With this characterization of each VIM, the Echo Control module can compute the optimal deployment strategy that minimizes the environmental impact of a given service. To allow users to access this mechanism, the NBI was extended with a new endpoint that enables green instantiation, sustainable instantiation of a network service. Instead of requiring the user to manually select a VIM to instantiate the network service, the endpoint requests the Echo Control module to choose the most sustainable VIM automatically. On the right, we can see how the VIM selection process works. When an OSM instance manages multiple VIMs, each with different CUE values, this can be due to differences in their energy sources. The Echo Control module selects the VIM with the lowest CUE, ensuring the deployment has the smallest environmental impact. Now I'm going to present a case study we conducted to evaluate whether the energy and carbon-aware mechanisms integrated into OSM can effectively reduce environmental impact. This use case was developed at Instituto de Telecomunicações and focuses on a maritime port video analysis scenario. So This scenario takes place in a maritime port equipped with a set of automated truck gates. Each gate is monitored by a surveillance camera that streams video over a 5G network. The goal is to automate the entry and exit of trucks while minimizing the energy consumption and carbon emissions of the supporting services. This process can be divided into two stages, the detection phase and the analysis phase. During the detection stage, the video stream is continuously analyzed by an image detection model. Its job is to identify when a truck arrives at the gate. Once a truck is detected, the analysis stage is triggered. At this point, a frame of the truck's license plate is captured and processed to validate whether the truck is authorized to enter or exit the port. The objective is to fully automate this workflow while making the underlying services as energy efficient and environmental sustainable as possible. We applied both of the mechanisms we developed in order to improve the sustainability of this scenario. To demonstrate the impact of defining different virtual energy aware states, we conducted an experiment to measure the power consumption of the truck detection service under various CPU configurations. We can see here on the right that, as expected, higher CPU frequencies lead to higher power consumption because they require increased voltage. Also, assigning more CPU cores also raises the service overall power usage. By characterizing the truck detection services, the truck detection service with multiple virtual energy aware states, OSM can trigger state changes based on power consumption. For example, if the C port is equipped with solar panels, perhaps the port needs as agreed to low carbon commitments. OSM can switch between the states depending on the availability of low carbon energy. Using these assumptions, we conducted an experiment to evaluate the carbon emission saving potential of the virtual energy aware states usage. The truck detection services uses the YOLO V8 TESS image detection model, which is continuously processing video frames to determine whether a truck has arrived or not. The experiment was carried out assuming the conditions of the port of Rotterdam, which is the largest port we have in Europe. We considered 20 truck gates, although the port of Rotterdam has many more, but we considered only 20. The video stream resolution was set to a low quality 360p resolution, since high quality video is unnecessary for accurate detection and would only increase resource usage, and we're trying to minimize resource and energy consumption. We assumed a 50% solar power contribution threshold to trigger the state changes. And finally, two separate states were defined. A standard performance state using 2.2 gigahertz and 8 cores, and an energy saving state that also uses 8 cores, but with a lower clock speed of 1.2 gigahertz. As shown here on the figure on the right, during the night and early morning, when solar power is unavailable, because it's night and early morning, the truck detection service operates in the energy saving state, resulting in lower carbon emissions compared to a scenario where the service is always running at a standard performance. At around 9 a.m., when solar power starts becoming abundant, OSM switches to a standard state. It continues like this until around 5 p.m., where, as solar availability decreases, OSM triggers another state transition back to an energy-saving state. It's the cumulative emissions throughout the day, with this graph on the right, showcases these effects more clearly. During periods of low solar availability, emissions grow more slowly. Overall, this leads to a 40.4% reduction in daily carbon emissions. The second stage we analyzed. During the analysis phase, we applied the spatial shifting mechanism. Since we assume the port does not have its own GPU-equipped IT infrastructure, it must offload the license plate analysis to a VIM, an external VIM that does. However, because GPUs are highly power hungry, the port aims to minimize the carbon emissions associated with this analysis. Therefore, it selects the VIM with the lowest carbon footprint. We conducted an experiment to evaluate the carbon saving potential of this approach. For the license plate analysis, we need an optical character recognition model that is capable of extracting text from images. In this experiment, we used Microsoft Tier OCR. The analysis is performed on 4K images since high resolution is required to ensure accuracy. We keep assuming the Port of Rotterdam scenario, and we consider 10,000 truck movements per day. These are the actual numbers from the Port of Rotterdam. And finally, we consider two separate VIMs. One that is powered by the standard Netherlands energy grid, and one that is powered solely by solar panels, solar energy. By deploying the analysis task on the solar-powered VIM, we achieve a 91.46% reduction in daily carbon emissions. When combining both mechanisms, the virtual energy aware states-based throttling, as well as the spatial shifting, we achieve an overall carbon emission reduction for the full scenario of 47.3%. Beyond the maritime port scenario, other use cases, and particularly other techniques described in the virtual energy aware state specification, can be explored to further reduce energy consumption and carbon emission. First, this paper on the left identifies inefficiencies in the power consumption of the 5G core, especially during idle periods. So techniques such as the CPU power states, as well as the spatial shifting mechanism, could be applied to improve the sustainability of the 5G core. Second, we have this paper on the right that shows that by adopting CPU pinning strategies to workloads, it not only improves the energy efficiency, but it can also enhance the performance by reducing latency and resource competition. These examples demonstrate that the mechanisms we introduced have the potential to improve sustainability across a wide range of different ICT scenarios. And that will be the end of my presentation. Thank you all for your attention, and I'll be happy to answer any questions you may have. Thank you.
Thank you very much, Filipe, for this nice presentation. Any question to Filipe? Yes, Luis. Go on, please.
Hello. Thank you, Filipe, for the nice presentation. My question is, I see you were mentioning that you consider multiple beams, and then you check with your eco control block, if I remember well, which one is the one with lower carbon emission, if I understood well.
Yes.
Are you considering, especially when you are considering this shift from one BIM to the other, the contribution of the network on these carbon emissions, maybe?
No, we're only considering the compute IT infrastructure, so only the server. The transport network, we are ignoring for now.
Okay. Okay, good. No, just out of my curiosity.
Yeah, but it's nice feedback, and we're looking into it. But it is complex to include the transport network. It requires interoperability.
Well, we have between OSM and TFS, so there are building blocks for that. I mean, if at some point you are interested, you know where we are for TFS.
Yeah. Thank you for the feedback.
Welcome.